Okay, so with our organic materials, we just about exclusively have gone to a steel back lining. It adds a little bit of weight, so that's the trade-off. But the benefit is that it's high burst strength. So now that I don't think we've ever had one of these come apart at high RPM. Now, people don't realize that it's not the RPM of the motor that is going to cause a clutch disc to blow up. Clutch disc is going to blow up because of the RPM of the clutch disc itself, which is determined by the transmission. So if you're coming into, say, a turn 2 or whatever, super sharp turn, and you downshift into second, but you're still flying in 4th, 5th gear speed, you've just zinged that clutch disc up to way beyond what the engine RPM is. It might send it up to 10, 12,000 RPM, and the friction material just blow off. But with the steel back, that prevents that from happening. So with the hub, it's really the details that matter. You can see the heat affected zone here from the induction hardening. We induction harden the spring windows to prevent wear from the spring rubbing inside of it. Now you notice the splines aren't hardened, and that's intentional. The whole hub is very tough, and it's I think it's about 30 Rockwell. But if we were to induction harden or otherwise harden the splines, now what happens is instead of the splines wearing on the hub, then the input shaft splines would wear, and we don't want that. I'd much rather have the splines of the hub wear, because this is a wear item, than the input shaft. So this is some of our raw materials, the clutch stampings, the castings. We get them from various sources. Some we have made exclusively for us. Some are factory components that we purchase. In some cases, we're taking the factory pressure plate, we disassemble it, and then we put our components in it, our stronger spring, remachine it to where the fulcrum's where we want it in order to increase the clamp load, and put it back together again. The diaphragm spring is really the key to a clutch. And by having the ability to make them here, it gives us a lot more parameters to work with when we're engineering a new clutch. In this case, we've added ribs, and we've increased the area in the finger in order to make it as rigid as possible, so we're not wasting travel when you operate the clutch. And that gives us more parameters we can work with elsewhere, whether it's giving it a little bit more Marcel, or if we want to lighten the pedal load, or increase the clap load. By getting more efficiency out of the diaphragm springs, it gives us the ability to tweak more knobs,
Maker making their own diaphragm, like we're one of the very few who do, is like an engine builder or tuner that grinds their own camshafts. If you can grind your own camshafts, you can do all kinds of stuff with an engine that a guy who doesn't grind camshafts is not able to. So with the tune and the cam timing and all that, that's what a diaphragm is for us. It's like the camshaft of the car.
That is what? Heat treating, or what is that?
Yeah, it's a tempering oven.
Tempering, okay.
So in this case, we're heating the parts, depending on what's going in there, we'll heat them up to 750, 800 degrees. It just depends on what we're processing at the time, but it's just nice to have your own oven to do that kind of stuff. For lower temperature stuff, we have an electric oven in here. This is a gas oven. So what Rob's doing here is he's inspecting the flywheel to see if it's within our specifications. He'll have a drawing and in this case he'll have on this one. Do you have a checklist set up on this one?
Yeah, it's actually there's already some predetermined specifications whether something's going to be within tolerance or not. So what I'm doing is Well, what I'm doing is I'm recreating the features of each of the different dimensions. They're already pre-programmed whether or not, or what the specifications should be, and then it's going to tell me once I measure them whether or not it's going to be in tolerance or not, and then we can determine from there if these are manufactured exactly to our drawing, or if there's any deviation from it.
So using the ferro arm, he's able to accurately measure each feature, and it's really easy to use. Go ahead and show them how you're doing it.
You start out by creating your base plane, which in this case is our crank surface, and then we base everything off of that. And we do it two different ways. We do a profile based off of basically what's considered a stack-up height. So the thickness and everything in between, as well as everything centered from the radius of the part.
Obviously, it's very critical to have concentricity be very accurate. And that's one of the things that he'll measure. He'll measure the dowel pins in relationship to the locating diameter where it locates on the crankshaft, because that has to be right. Otherwise, the whole clutch, if the clutch isn't centered, then it's going to affect the balance of the whole assembly. All right, so this is one of the drive plates for our solid center clutch disc, where we'll attach the cerometallic material on there, or metallics. And in this case, we're stamping it with we're staggering the buttons so that these buttons will be at a little bit different diameter than the other three. And that way it covers more surface area on the pressure plate and on the flywheel. And so you're distributing the load and the heat and the wear over a greater area of the mating surfaces. And we also can take the same part, and using the other punch press, we can punch the center out and use it for spring center applications.
Back to the story on these machines. This is there's a lot of equipment out there that does a lot of things with, feature. It's like phones and washing machines. A lot of features. All these, more or less, not what it used to be.
Okay.
This is a older, heavy-duty, massive machine. Adding a laser curtain and all kinds of safety features to it that it never came with. So we've modernized these machines.
So we're going to change this from a solid center to spring center with one hit. Crazy. See, this one has a
how quickly an engine can accelerate the drivetrain. Because you lose horsepower. The more inertia you have in the drivetrain, that takes horsepower to spin all that up. And that's not going to the rear wheel. It's being filtered before it gets to the rear wheel. So the inertia is very important to know how much loss you're going to have in your drivetrain. So it's important for us to make sure we're comparing the stock flywheel, our street light flywheels, were appreciably lighter, and then our pro light flywheels, which are rigged for the track. Mm-hmm. That's why we make many applications. We make both versions, because what's good on the street, the optimal street inertia, is not the best for the track. It's too heavy. But a track flywheel is definitely too light for the street. It's, stall it more often. It's going to be a lot more vibrations going to be transmitted. So there's different applications. We have different inertias, and this machine directly measures inertia of the flywheel.
How does it do that?
Can you explain how it works then?
So essentially we have a long torsion spring underneath that adds the resistance. So you put a part on top, clamp it down, and as you turn, it puts tension on the spring, and it's timing how long it takes bounce back and forth. So I'll demonstrate with this flywheel. So it just bounces back and forth. Move it up, tell it to run, turn it, and just let it bounce back and forth. It's measuring, doing the math, and spits out a number right there. And so this one, for example, is 199 pounds square inches, which is the unit for moment of inertia in this case.
You could have 2 flywheels that weigh, say, 12 pounds and have as much as 25 to 30 or 40% difference in inertia depending on how the material is distributed away from the center of the flywheel.
At a molecular level, you're talking about like
By design.
by design.
Right.
Do you have-
So a 9-pound aluminum flywheel and a 12-pound steel flywheel, that's not enough information to know what the engine's going to see for resistance. The moment of inertia is what the engine sees. It doesn't care if the flywheel is steel, aluminum, titanium. It doesn't care at all. What it cares about is how much energy does it take to spin it up, and that's a function of the density of material and the mass displacement or placement from the center of the rotation.
And this tool, is it a proprietary ACT thing, or
Well, we made it. We designed it and built it. So I guess you could say yes.
and how did you even know that you needed something like that?
Well, again, inertia is a fundamental physics part of drivetrain acceleration. So you have to know these bits of information when you go to tune. When you take a big, heavy, dual mass flywheel off of a vehicle and you replace it with a lightweight flywheel, you have to know what impact are you making? How significant is that impact? And that's why we have the 2 different levels of flywheel, the street light and the pro light, because we want to make a certain impact with the street light flywheel, but on the track you want to go even more. So we know how much more we want to make a pro light flywheel than a street light. So we'll separate that. And the inertia is the defining factor, not the weight.
I'm going to demonstrate our broaching machine. This is how we cut splines into the hubs of our clutch disc. It's a pretty simple machine. Basically, you're just pulling a tool through the part, and it cuts the teeth for the splines. It's a loud machine too. We're changing to a tubular rivet motor right now. Start experimenting. Charlie.
surprised me these things have shields around them. How many RPM is it? And that's enough for the trick?
Very sensitive machine. It's sensitive.
Okay. Alright. If you're lacking representative RPM, it makes about 450 of the machine.
Oh yeah, the sensors in there are extremely sensitive. The tightest OE tolerances out there on the market that we could find, we're balancing to 50% of that. So we're twice as tight as the tightest OE tolerance out there.
Wow.
We're expecting, we don't know, every place we go, distribution, we don't know or someone's going to go race it. You know, we don't know. So we have to see if we go on a very high
For laser open environment. We did that so that we can do it faster. A lot of the laser machines, can be glass. So you got some glass.